Okay, we're going to move forward here, and we're going to start to talk about some things that are a little more advanced than what we have been focusing on here the last few weeks. Now, basically, we kind of had the opportunity to go through and look at a number of different kind of prerequisite type things that should help us with this next section or some of the next topics that we're going to cover as we move forward here. Now, what we're going to do is we're going to take some of that translation and transformation stuff that we did with both linear functions and absolute value functions, and we're going to apply them to what are known as quadratic functions. So basically what we're looking at doing here is we're going to transform those quadratic functions just like we did with the linear functions and the absolute value functions like I talked about before. On the bottom here, this might look different or something that you're not really used to seeing. But if you compare it to what we talked about as far as absolute values are concerned, it looks somewhat similar. All right, now obviously we're going to have to explain a little bit about what that is there and also what this in front happens to do. All right, but again, we're not really changing a whole lot from what we have already done before. All right, some of the key terms that we're going to talk about, obviously we're going to have to figure out what a quadratic function is. For those of you that don't know what a parabola is, we'll explain that a little bit. We're going to talk about vertex and vertex form. We've already talked about what a vertex is when we talked about absolute value functions. It's either going to be the top or the highest point of your parabola or the lowest point of your parabola, depending on whether that happens to open up or it happens to open down. Okay, so we're used to seeing things in this form, known as linear form, also slope-intercept form. But the whole idea is if you have something in that form, you graph it, which we talked about before, you're just going to get a straight line. Okay, you can go up, down, side to side, positive slope, negative slope, but it's not going to be curvy or wavy. You're going to have a straight line. Okay, a quadratic function, which we already saw this on one of the previous slides, has a little bit different, properties, and we take a little bit different approach to it. Now, the first thing that you will obviously notice about this is there's a power of 2 in here, and that basically is what defines a quadratic function. A quadratic function is a function that can be written in this particular form that I underlined here, and the variable is always squared. Okay, that's a key in determining the difference between something that's linear, like I have up here, or something that's quadratic, is the fact that you're going to have something that is squared, or the variable is going to be squared, I should say, in a quadratic function. Okay, so what we're going to talk about now is just kind of comparing what are known as the parent functions, or what we call the base functions of each of these types of function. Okay, so when we're talking about linear functions, the parent function would just be f of x equals x, or y equals x, if you want to think about it that way. All right, we have a slope of 1, we have a y-intercept of 0, and you can see over here what that looks like. Now, every transformation, every translation that we apply to that particular function basically starts with the base function. We start with that base, and we apply different things, moving it left and right, up or down, stretching and compressing. We do all that to the base function. Well, it's really no different with the quadratic parent function. Everything that we do, every transformation that we apply, is going to be applied to, or you can think about it as being based on, what this parent function is, or basically the base function for quadratic functions. All right, so everything that we're going to start with is going to look like a parabola that looks like this, that happens to have these particular values as characteristics of it. Now you'll notice this looks very similar to what's on your note-taking guide. All right, so it would be important to make sure you fill this out because you're going to be comparing things to that as we move forward and move through this. Now, if you're not familiar with what this U-shaped graph is down here in the corner, that is referred to as a parabola. Anytime you graph a quadratic function, you are going to get a parabola. Now, the properties of that parabola can change a little bit, especially if we start stretching and compressing it. But if we are simply just moving it left or right, or moving it up and down, or reflecting it, the dimensions of your parabola are going to be as is, or as you see right here. These will be, the same dimensions as far as what we're going to do, moving it left and right, up and down. And that's kind of where we're going to move into shortly. All right, now eventually when we graph these, there's all sorts of tools as far as graphing calculators and stuff that you can use to graph a quadratic function, just like you could use it to graph a linear function. All right, what we're going to start off with is, how do you graph these, or what can you do to graph these if you don't have that type of technology or software available to you. So basically we're going to approach this the same way that we approached linear functions when we didn't know what slope-intercept form meant. We're going to pick x values, all right, which you can see on the left-hand column of my graph right here. I already have designated some of those that we're going to use. We're going to fill those in, and we're going to figure out what's going to come out, or basically get a y value out of that, and we're going to use those to plot the graph. So if I'm going to start with 0, essentially what that's telling me to do is I'm going to take f of 0. So wherever there's an x, I am going to fill in a 0. Well, that one becomes fairly easy. We're just going to end up with 3. Okay, so I fill in 0, I get 3 out. Now, based on what's written up here, technically it wants you to write the full point, so 0, 3. But we did get 3 out of this. Okay, then we do the same thing with the 1. Take f of 1. I'm going to fill a 1 in wherever there happens to be an x. Okay, so I'm going to get 1 minus 4, which is going to be negative 3, plus 3 is going to be 0. Alright, so I fill in 1, I get out 0. Okay, and we can continue on down here, and I'm not necessarily going to go through all of these because I think we by now should get the general idea of how this is supposed to work. Alright, but if we fill 2 in, we get 4 minus 8, which is negative 4, plus 3 is going to be negative 1. So I have the point negative 1, or excuse me, I have the point 2 because I filled 2 in first. Alright, 2, negative 1. Okay, would be my next point. Alright, so if you fill out the complete graph here, the complete chart, alright, you're going to get different points. You just have to be careful and make sure that you are getting the correct signs, especially when you start dealing with this particular section of your table, because one wrong sign and all of a sudden you're going to get the wrong point, and all of a sudden you're going to get something that doesn't necessarily look like a parabola anymore. Alright, so like I said, you could move forward, continuing down, getting a few more points for that particular graph. I'm going to stop right there just so you don't have to watch this forever. Alright, but if we would get those points, you can see that you would be able to plot those 5 points on a particular graph, and you would be able to tell basically what your graph is going to look like. Now, the 3 that we graphed, or the 3 that we figured out based on our table, would have been those 3 right there. If you would have continued on, you would have been able to figure out what the other 2 were as well. Okay, so what I want you to do now is I would like for you to pause the video again and kind of work through and see if you can get the correct points for this particular equation or function based on what you're going to fill in. Give it a try to graph it. Alright, then you can come back and we'll actually go through this complete problem, and we'll see how close your graph is to the graph that I happen to get up here. Alright, now hopefully you had a chance to work through all this. I'm going to kind of start here writing everything out so you have an opportunity to kind of check things with your particular work that you have down. Now, another thing you need to be careful of right here is the fact that negative x squared up here, there is a difference between this and this. Okay, and as you can see, as I filled in right here, you need to take the -1, fill in, square it, and then make it negative after the fact. All right, if you don't do that, all right, you're going to end up getting the wrong number as we move forward here. So if I look at this, I'm going to get +1 when I square the -1, then I make it -1. So -1 plus -6 is going to be -7 minus 8 is going to give me -15. So I filled in -1, I got -15 out. Okay, and this one you can see our numbers get a little bit bigger, so it's going to vary a little bit as far as how big or how small something happens to be after we go through all this stuff. Alright, so now I'm going to fill +1 in. You'll notice there's not really a whole lot of difference here in how we start. We square the 1 and get 1, but then we have to make it negative, so we have -1 but +6 this time. So I'm actually going to have a +5 minus 8 is going to be -3. Alright, so we filled in 1, we got -3. Alright, moving down, g of 3. Alright, we fill in 3, square it, 6 times 3 minus 8. Okay, well, square the 3, you get 9. You make it negative because of this sign out in front. So -9 plus 18 is going to give me +9 minus 8 is going to give me 1. So I filled in 3, I got 1. Okay, now going the other direction, moving along here. We fill 5 in, and you can kind of start to see how this process, it's not the most convenient thing in the world because it takes a lot of time to go through and try to fill all this stuff in. So once we get into, allowing you to use a graphing calculator and stuff, it's going to make things a lot easier. All right, so filling in 5, we get 25, make it negative. So -25 plus 30 is going to be +5 minus 8 is going to be -3. All right, then the last one, g of 7. We're going to square the 7. 6 times 7 minus 8. All right, we'll get our 5th point that we can work with here. So 49, make it negative. So -49 plus 42 is going to be -7 minus 8 is -15. Okay, so hopefully you were able to get all those points. Now the other thing that you'll notice is the points that we pick out on the left, or the values of x we pick out on the left, we pick those out for a reason. Because this center one, you can tell, is going to be your vertex, okay, or the highest or lowest point, depending on whether it opens up or down. And you'll notice that the y values over here kind of match up the same distance away they are from the vertex. And that's because parabolas, or what we get when we graph these, which you can see right here, if we take all those points, and again, this is going by 2's for each block, okay, but you'll notice that we have all our particular points that happen to be on there. And the thing that you'll notice, like I said, is the fact that it's symmetrical. You have points that are the same distance away on both sides and all that fun stuff. Okay, now once we kind of get a grasp of how that's supposed to work, we're going to kind of get into stuff that we should be fairly familiar with. And what that deals with is moving things left and right, translating things. Okay, so again, you just have to follow what the formulas here on the board tell you to do. Okay, right here, and these formulas really haven't changed, especially what happens to be on this side. All right, if you're moving something left and right, you have to make that shift along with the x input. Okay, so remember, in here, if it's minus something, that actually moves it to the right. If it's plus something, that actually moves it to the left. And again, just like always, vertical translations are always a lot easier because you just take that number that you're either adding or subtracting, what you're going to go up or down, and you just add it to the end of your particular function, or add it to the function as a whole. Okay, so what we're looking at here is it says use the graph of f of x equals x squared as a guide and describe the transformations and then graph each function. Okay, well, if we're using this as a guide, okay, and you can kind of see that same graph is on the coordinate plane on the right there, we basically just need to explain what's going on. So the first thing I notice is this in here. Okay, there's a -2 along with the x, meaning we're changing our x input value. Well, -2 means we are actually shifting the base function, our parent function, we are shifting 2 units right, and the +4 means we are going 4 units up. So essentially we are taking the graph that is already graphed for us over here on the right, and we are shifting it 2 units to the right, and we are taking and shifting it 4 units up. So my new vertex is going to be right here. Okay, now the dimensions of everything else have not changed. So I just kind of take a look at where my other points happen to be down here. Okay, I had a point, up 1, over 1 in both directions away, so I do the same thing over here. Then my next one kind of took me over 2 and up 4, back 2 and up 4. So I'm going to go from our starting point over 2, up 4, over 2, up 4. Okay, or back 2, up 4. And that gives me a pretty general idea of what my graph of the translated function should look like. Okay, so again, once you figure out essentially which way you're shifting, left, right, up, and down, okay, you get a better idea of where your graph should go. And again, the overall dimensions of your graph have not changed because we're not stretching or compressing anything. We're just taking the graph and we're simply moving it around the coordinate plane. That's why I was able to compare the dimensions of my original graph, or some of the points where how they related to the vertex, and just basically draw the same graph in a different spot on the coordinate plane. Okay, so again, let's look at another example. All right, and I'm not going to worry too much about you working these out on your own, simply because it's very similar to what we have done in the past. So again, I'm going to look in here. It's a +2 this time, so that means I'm going 2 left, and a -3 back here means I'm going 3 down. So essentially I am taking, again, this parent function, or this base function, and the same picture or the same graph that happens to already be over here on the right, and I'm just taking it and I'm moving it 2 to the left and 3 down. So my vertex is now going to be here. And again, the dimensions of everything else have not changed. So I can go, let's see, over 1, up 1 on both sides of it, and over 2, up 4 again, both ways. Over 2, 1, 2, 3, 4, back 2, up 1, 2, 3, 4. Okay, so again, same dimensions as my original. All right, it's just located in a different area of the graph. Okay, and I know my lines aren't fantastic as far as what they're going to do there, but you get a pretty general idea of what the graph should look like. Okay, fairly similar looking, based on a little human error there, to what was originally graphed there. We just move it to a different point on the coordinate plane. Okay, again, very similar to what we're talking about before. I'm not even going to worry too much about graphing this one because we're just moving that graph again. But we're looking at this right here again. That tells me that I'm going to go 3 units to the left because it's +3 and it's opposite. And the -2 back here tells me I'm going to shift the graph of my parent function, my base function, down 2 units. So essentially, I will have this same graph right here, but it will be starting at that point down there. Okay, so same exact graph, same exact dimensions, just starting in a different area. Okay, so again, that should be very, very similar to what we had talked about before with both linear functions and absolute value functions. Okay, and remember, we can move things left and right, we can move them up and down as far as translations are concerned, but when we're looking at this now, remember we can also reflect things, stretch them, and compress them. Now reflecting with parabolas is fairly simple because they're symmetrical, okay? And we know we flip-flop back and forth, up and down, it's not a big deal. The overall dimensions of your graph stay the same when we're talking about reflections. All right, when we start stretching and compressing, then we have to do a little bit more work because that's probably going to require us to take and fill in some different numbers to figure out just exactly how our graph has changed. Now again, these particular images, these particular equations should look very, very familiar to you because they are the same thing. We're applying the same type of rules, the same type of operations, just to a little bit, slightly different function. Okay, so you can see again reflection across the y-axis. All right, you're probably not going to notice a whole lot of a difference if your graph is centered, but again, you're changing the x values. Okay, so it has to put a negative in with the x wherever there happens to be one. Across the x-axis, okay, we just change everything in the function. If it was positive, we make it negative. If it was negative, we make it positive. All right, same rules apply down here when we're talking about horizontal stretches and compressions, okay, and vertical stretches and compressions. And this seems to be the one that we tend to struggle with the most. All right, we can't seem to keep track of when do I fill it in with the x and when do I fill it in, or not fill it in, but when do I take it times the entire function that's there. And that's something we got to do a better job of getting straight because it throws off a lot of our final functions that we're supposed to get. And with the horizontal ones, just remember down here, it's kind of, they're inversely related. And that's why whatever our factor is, like say we're going to, we want to compress by a factor of 2 horizontally. 2 goes in here, and essentially what we end up filling in is 1/2. Okay, so just something to keep in mind, as we move forward here with this a little bit. Okay, now, again, we're always going to compare everything to our parent function or our base function. Okay, so using the graph of f of x equals x squared, describe the transformations and then graph each function. Okay, so graphing here, it's going to require a little bit kind of different approach. There's a couple different ways we can think about it. I'll get into here in a second. But first thing I should notice, there is a negative right here that happens to be out front of everything that happens to be there. Okay, so a negative out front basically means there should be some type of reflection. In this case, because it's outside of the squared part, in front of everything, we're talking about reflection across the x-axis. Okay, and the 1/4, again, if it's not inside with the x, okay, or we don't have parentheses around it, all right, in this case, it doesn't look like this. Okay, it's written differently over here. This on the right would represent some type of horizontal stretch or compression. In this case, because it's outside of the squared part, we're looking at some type of vertical compression. All right, and the reason that I call it a compression is because we have a fraction. So essentially what it's going to do is if you take a fraction, like 1/4, something that's less than 1, and you multiply it by the entire function, it's going to compress things, or you're not going to get as large of output values as you typically did before. Okay, so if we look at both transformations that are being applied here, there's a couple different ways we can go about trying to figure out where our graph is supposed to be. The first would just be to simply kind of take some values and fill them in for x like we did before. Now, because my graph over here is centered, I might just start with 0, 0. So I'm going to take 0 and I'm going to fill it in place of the x. Okay, well that becomes pretty easy. I'm going to get 0 out. So I fill in 0, I get 0 out. My starting point for my new graph is still going to be at 0, 0 or at the origin. Okay, now where things are going to change a little bit here is when we start filling in other numbers. Okay, now picking the next ones, it kind of depends. You start picking some fractions, or excuse me, like numbers like 1 in this case. It's okay to pick 1 and -1. We want to pick on both sides, but it might be a little bit easier to pick something bigger because of this fraction that's out front. The other thing that you can kind of do here, and it kind of helps you, it's almost like a way to cheat a little bit, is because parabolas are symmetrical, you really only have to figure out points on like what would be 1/2 of your parabola, because the other side is going to mirror that. So then I can just match them up with how far they are away from the center point. Okay, for example, if you look at the graph up here that's already drawn for us, if I were to split that down the middle and say I figured out on the right here, well, my first point is 1, 1. I don't have to do anything to figure out that my other point is going to be over here, because I just look for a point that is the same distance away from that center line. Okay, so what I'm going to do here is I picked 0. I'm going to go g of, let's see, how about I go g of 2? Now the reason I'm going to pick 2 is because when I fill that in right here, if I take 2 and square it, I get 4. Now, in some cases that might not be the best number to work with, but here 4 times negative 1/4 actually gives me negative 1. So I keep things a little bit easier to work with because I don't have fractions. So I'm going to go over on my graph. I filled in 2 and I got negative 1 out. So 2, negative 1. Now again, I am basically 2 units away from the center line that I drew. So I can draw that same point over here because it's symmetrical. Okay. Now the next one I'm going to pick is I'm going to pick 4. Just because, again, it should be something that's a little bit easier to work with. So 4 squared is 16 times negative 1/4 is going to be negative 4. Okay, so I filled in 4. I got out negative 4. Okay, so I'm going to have a point that's right here. And again, pick a point, same distance away on the other side of my parabola. So now, I'll try to draw this in as best I can. Okay, you can see how not only did I flip my graph over because of the reflection over the x-axis, but I also compressed things, or you can see how it's a little bit wider. You could think about it as, basically we took each of our y values and we pushed them down a little bit. All right, so they're not, each side of my parabola is not increasing, or in this case decreasing, quite as rapidly as my original graph happened to be. Okay, now like I said, a lot going on here. You just got to make sure you stay calm a little bit and think about what's going on and think about what numbers are going to work. Now again, I used 0, 2, and 4 to fill in to find my new function. You could have used anything you wanted to. You could use 1 and 2 if you wanted to. The thing about a 1 in this case is you would end up getting, an output value over here on the right that probably would have been a fraction. And again, you don't have to fill in 5 separate numbers. Okay, focus on 1/2 of your parabola like I did here. I just focused on everything that was on this side. All right, so I filled in 2 and I filled in 4. And because they're symmetrical, like I said, same distance away from the center, all right, I just pick a point and I mirror it on the other side of that particular parabola. So you save a lot of time and a lot of energy by doing things that way. Okay, now I'm going to take one more look at this and then I'm going to give you one I want you to kind of try on your own a little bit. But here you can see already the difference in what we had last time. We had something that looked like this. In this case, all right, you can see how the 3 is inside with the x. Okay, what that tells us right away is we're not talking about something that's vertically stretching or compressing anymore. We're talking about something that's horizontally stretching or compressing because it's in with the x. All right, the other thing to keep in mind is remember when we're horizontally compressing something, and I'll just use g of x in this case, it's 1 over b in with the x. So if I end up with a 3 here, okay, what that's telling me is that what I probably filled in for b down here was more than likely 1/3. Okay, because 1 divided by 1/3 would give us 3. So what this is telling us is we have a horizontal stretch or compression by a factor of 1/3. Okay, so that would be how we would describe the transformation here. All right, because it's kind of like I said, it's that inverse relationship there. So if I'm getting a 3 here, that means my factor, my b, had to have been a fraction to begin with. So I just have to think about, how do I get 3 here? Well, 1 divided by what gives me 3? Well, that would have to be 1/3. Okay, now again, this one should actually be a little bit easier to graph than the last one because we don't have to worry about flipping things up and down. And the 3 that's in here happens to be a little bit easier to work with than what we had before with that 1/4. So again, I'm going to start with 0. Anytime you can start with 0, that's probably the best case. And the other thing you'll notice is we don't have anything being added or subtracted in with the x, or anything added or subtracted from behind. So what that tells me is I'm probably not moving. More than likely, I'm going to have the same starting point as the graph that's already there for us. But just to check, I'll go ahead and fill in and see what we get there. Okay, well in this case, 3 times 0 is 0, 0 squared is 0. So I do in fact have the same starting point as what happens to be on my graph already. Okay, now the next one I'm going to pick 1. I'm going to try to keep my numbers a little bit smaller because otherwise I'm going to run out of room on this one because of that 3 in there. But 3 times 1 squared. Well, 3 times 1 is 3. Square it, you get 9. Okay, so you can see here when I fill in 1, I get 9. Okay, 1. See, the problem we're going to run into in this is I'm going to run way, way off my particular graph that happens to be right in here. All right, so I'm going to go ahead and do the best I can. So 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. So up here under the word compressing, that would probably be where my, my first point would be. All right, and that's the problem that you run into sometimes with this. And I just picked a point that's about the same distance away on the other side of the line that would split my graph in half. Okay, so that's a problem with picking 1. So in this case, it might not be a bad idea to maybe pick something like 1/3. So I pick 1/3. 3 times 1/3 gives me 1, and then I square it, I can get 1. So the problem with that is, 1/3 up 1 is probably going to be in here somewhere, and then I can pick a point the same distance away from that center point on the other side. Now you can see with this, and this is going to be really tough for me to draw in, we really compress things horizontally with that factor of 1/3. Okay, everything got super skinny in there. Okay, so again, you could have filled in whatever you wanted to as far as your points for x. I picked 0. I filled in 1. You notice how we got a really big number out. So that's why I went back with 1/3 or something that was a little bit easier to work with, that 3 in there, and I got 1. All right, but you can see how, again, that's really compressing things horizontally. Okay, now this goes back something similar to what we started with. So again, I want you to pause, take a look at this, see if you can figure out what translations or transformations are being made first, and then go ahead and give it a try, see if you can graph it on your own and see what it looks like. All right, hopefully you had a chance to do that. We're going to go ahead and look at this to begin with. Again, very similar to the first example we talked about when we had the negative 1/4 x squared. So the negative out front here in front of the entire function indicates that we're going to reflect across the x-axis. Or essentially, instead of opening up, my parabola is going to open down. And the 1/2 in here indicates that we have a vertical compression by a factor of 1/2. Okay, so essentially every output value that happens to be on this top graph here is going to get shrunk down to half of what it would be. All right, so if I think about the point 2, 4, well, that's actually going to become the point 2, 2. And then if I reflect it over the x-axis, it would end up being down here somewhere instead. Okay, and that's another way you can think about this, as far as if you understand that essentially, if we think about an xy point on our original graph, and then we apply these translations to it, the negative is going to make this y negative, and at the same time we're going to reduce it by a half. So essentially, if you pick points off our original graph that are up there, say for example we start with the point 1, 1 that happens to be right here. If I apply it to what I've decided that's going to happen up here, the x isn't going to change, so I'm still going to have 1, but I'm going to take that y value and I'm going to make it negative and switch it by half. So I'm essentially going to end up with 1, negative 1/2, or negative 1, negative half, as my points after the vertex that happens to be in there. Okay, or if I would think about, we talked about the point 2, 4 up here is on my original graph. If I think about putting that in here, I get 2, but if I put the 4 in for the y, I'm essentially going to end up with -2 as the point on my new graph. All right, and that's why I kind of highlighted, that spot down here and over here again. But just to double check here, we can fill some points in. So I'm going to go again g of 0 to begin with, because that's probably the easiest one to work with. And you can see you're going to get 0. So when I fill in 0, I get 0. That's why I have my starting point or my vertex down here as 0, 0. Let's go ahead and fill in 2. So -1/2 times 2, we square it. All right, 2 squared is 4 times -1/2 is going to be -2. And that's why I already have the point 2, -2 on my graph. All right. I'm going to go ahead, I used 1 when I was doing some of my comparisons earlier. I'm going to go ahead and pick something a little bit bigger. I'm going to go with 4. So -1/2 times 4 squared. 4 squared is 16 times -1/2 is going to be -8. All right, and again, that's probably a little too big because I'm going to run off the bottom of my screen here. But 4 -8 would probably put me way down here close to the bottom of the screen. Same thing over here, point same distance away. All right, so again, it gives you a general idea of what it looks like my graph is going to do. Not going to be perfect, all right, but you get the general idea. So again, we took this graph that's up here already. We were reflecting it across the x-axis. That explains why it opens down. And then we were compressing it by a factor of 1/2. So that's why you can see how it doesn't go up quite as fast, or it doesn't. It's going to be just a little bit wider than what we happen to have on the top. Okay. Now, we've already talked about some of this a little bit. Okay. Parabola opens upward. That means that its lowest point is the vertex, which also happens to be a minimum if you're thinking about the range. If it opens down, that means its highest point, or the top of it, is your vertex. And it also means that happens to be a maximum if we're talking about domain and range, particularly range for these functions. Okay. Now, we talked about vertex form a little bit at the beginning. Just like it was with absolute value functions, the h and the k are going to represent the coordinates of your vertex, okay, where the lowest point or where the highest point on your graph is going to be, depending on whether it opens up or down. A is just going to affect a little bit as far as, one, if it's positive or negative, does it open up or does it open down? But on the other side of things, it can also affect how wide or how narrow something happens to be. So this, again, something that shows up in your notes. Okay, you want to focus a lot on the h and the k. Okay, remember h, the signs are a little bit backwards. Okay, if it's minus h, that means it's actually a positive x value for your vertex. Okay, a, like I said already up here, that just kind of dictates, more or less if it's going to open up or down based on whether it's positive or negative, and possibly whether it's going to be some type of vertical stretch or compression, depending on whether it's a fraction or whether it happens to be a whole number. All right. So again, very similar to what we talked about with absolute value functions. Okay. Down here at the bottom, this is somewhat helpful too. If we talk about the parent function, if you apply what happens with what a parent function looks like when you graph it, as far as having 0, 0 be the vertex, the h and the k essentially fall out of that equation, and the a is just a 1. So we end up with f of x equals x squared is more or less your vertex form for that particular equation. And that's basically what we're talking about down here. Is anything written in this form, we refer to that as the vertex form for a quadratic function. Okay, so now what we're trying to do is, similar to what we did last unit a little bit, is use a description to write the quadratic function in vertex form. Okay, so we're going to take what we know about this and we're going to apply the different transformations listed in the problem to that, and we're going to basically come up with a new function that we're going to call g. Okay, so we're going to take that parent function and we're going to vertically stretch it by a factor of 4/3. Then we're going to translate it 2 units to the left, and then 5 units down. So this becomes a little bit easier because if we're vertically stretching, that just means the 4/3 goes in place of your A. All right. Translated 2 units left. So if we go 2 units left, remember it's opposite. So it'll be +2. And down 5 units, it's going to look something like that. Okay. So again, most of what you're going to deal with quadratic functions is some type of vertical transformation, vertical compression, vertical stretch. So I can more or less just take that vertical number, that 4/3, and put it in wherever the A is. All right, and then moving left and right, up and down, very similar to what we did before. Okay, if you wanted to compare the two graphs together, your parent function would be represented by this line over here. If we apply the transformations, and you can kind of see that in here, that -5 at the end there too. That's what your new graph would look like if you were to actually go ahead and do that. And the reason we use a graphing calculator in this particular one, just kind of prove that we were correct, is the fact that when you start getting numbers like 4/3 in there, filling in numbers by hand gets to be a little bit kind of a pain. Okay, here's another example. Okay, now I want you to pause your computer again, pause the video, and think about what would happen. Give me something in vertex form at the end here that we can take a look at and compare to what I get. All right, so same idea here, and we're going to take our function, we're going to name it g of x, and essentially what we're going to do is we're going to just kind of fill in for a, h, and k here. Okay, so again, it says it's vertically compressed. Anything vertical means that's what's going in for A. Okay, so I can start with that right away. We'll say 1/3, and then we're going to go 2 units to the right again, or 2 units right this time, so we go -2, and 4 units down, we go -4. Okay, so again, because it says vertically compressed, we can just write that number out front. Okay, if it was horizontal, okay, then we'd have to start filling stuff in with x, and that would change what we got going on here a little bit. But anytime it says vertical, a lot easier. Just write that number out front. That's going to be your A value. Okay, and then the 2 and the 4 that fit in there, very similar to what we've done before. Again, like I said, with absolute values. Okay, in this case, again, we're just comparing the two. Okay, what does it look like if I shift something 2 units to the right, 4 units down? Okay, or essentially I've moved the vertex to -4, and we apply a little bit of a vertical compression to it. So you'll notice how it widens out a lot faster than it does go up or increase. All right, now a couple story problems in here, and the thing about the story problems with this chapter is they're not overly difficult. We're basically just taking some type of equation, like in this case, that we're given to begin with, and we're just going to talk about what happens if the number in front of it changes a little bit. Okay, so if we look at what's given here, okay, we got a problem here. It says this function that I boxed in up there talks about the distance in meters that a dropped object falls in t seconds is approximated by d of t equals 4.9 t squared. Okay, on the moon, the corresponding function is d, and the little m just means on the moon, of t equals 0.8 t squared. What kind of transformation does this change from the original function, and what does the transformation mean? Well, obviously, in this case, we're looking at, we go from 4.9 in front to 0.8 in front. Okay, what that's doing is we're talking about something that's vertically affecting that particular function. So if we decrease that number from 4.9 to 0.8, basically what we've done is we've almost kind of applied a vertical compression to our graph. All right. So what happens with this compared to the original one that we have over here is that this graph is probably going to be significantly wider than the original, which was probably going to go up a lot faster. Okay, and basically what that means is if you drop something on Earth, it is going to drop a lot faster, okay, or you're going to gain a lot more distance than you would if you drop that same object on the moon. Okay, it's not going to go as far, and that basically just has to deal with gravity. Okay, and here, just graphing one half of that parabola, you can see how the moon one is obviously wider and does not go up near as fast as the other one does. All right, here's another example. I'm just going to kind of walk you through this one again. But basically, we're looking at the same type of situation. We're given an original function, excuse me, and what we're doing is when we put basically what it is, we put new tires on something, and the braking distance, which is represented by the original boxed equation up there, now becomes what we have down here. And you can see how the number, again, in front of the function, or in front of the v squared in this case, goes down a little bit. All right, you're going to end up with the same type of transformation that we had in the last example problem. Basically, you just have some type of vertical compression. So the graph of your new function is going to be just a slight bit wider, or not go up quite as fast as the original function. And you can see that in this particular equation or graph down at the bottom. So again, with our story problems, the big thing that we're looking at is just the simple fact that we really don't have a whole lot of work to do with those. We're just applying the same concepts that we did with the other problems throughout. Okay, now again, I know this video is significantly longer than some of the other ones we have done. That's part of the reason why I'm only giving you this one assignment for the week, and giving you a chance to kind of sift through a lot of important information that's going to help us as we move forward with the rest of this particular chapter.